Welcome everyone to the Multilin 850 webinar. The agenda for this evening is we'll do a quick overview of the Multilin 850, and then we'll go into the hardware aspect of it and then the software aspect. Can everyone see my screen? Hello? And can everyone see my screen?
Yeah, I see it. Great.
Terrific. Okay, we'll begin. So this is our introduction to the Multilin 850. So what is it? The Multilin 8 series platform is GE's next generation global protection and control relay platform designed for industrial and distribution utilities. So we're hitting all the different application types with the new 8 series. That's going to be, I don't want to say replacing the SR series, but heavily competing with it. The 8 series platform is going to be targeting the oil and gas, mining and distribution utilities applications, and it's going to provide more asset management for critical feeders, motors, generators, and transformers. Now, there's a couple of key points here. So we're going to differentiate from a value proposition by delivering the highest level of quality, reliability, and performance with the following topics. We've got innovative technology and design, interoperability, detailed diagnostics, exceptional quality and reliability, and service and support. So let me highlight something from each one of these categories. So one of the biggest things under innovative is the elimination of the electrolytic capacitors. This is a huge change for us because at this point we no longer have to have scheduled power up of the relays to exercise the electrolytic capacitors. We have field swappable power supplies. We have low insertion forced rail construction. From the interoperability part, we have a secure Wi-Fi communications that provides simplified connectivity. We have the latest in cybersecurity that complies to the NERC requirements. We've improved the electrical system insight with 128 samples per cycle, 8 times the sample rate compared to traditional relays. From the exceptional quality and reliability, the big thing that sticks out here is that we've now designing all our PCBs to IPCA 610 Class 3 manufacturing standards. And from a service and support point of view, the big key here is that we now have a 10-year warranty plan in place. And this is not just for this product, this was with all our products. All right, so what I'm going to do is I'm going to step now into the 3D model for the Multilin 850. I'll talk about some of the features that we have. Well, I'll start with the front first. So first of all, we have our local display. You can see we now have a large display that shows a lot more data. This is a 5.7-inch graphical color display that you can see shows a great deal more detail than our standard 2 lines of display. We have push buttons that go into all the different aspects of the menu. We have targets, which are our fault conditions. So once we press this button, it'll display what we have as fault conditions. The clear will clear the menu from this point. Over here on the right, we have our home button and our escape button. The home button will bring us back to the main screen. The escape will take us back 1 level. So if I press the escape, I'll come back 1 level. If I press the home, we are already at the home screen right now. If we go to status, we can monitor statuses of breakers, contact inputs, output relays, virtual inputs, virtual outputs, information, device status, the clock, and the auto reclose. So what happens here is everything that's listed here is now based on the buttons along the bottom. After virtual inputs, we push the double arrow to the right and it'll display the rest of these items. So let's take a look at what the virtual inputs look like. We have, this shows the states of the virtual inputs being off, on. If we go back a screen, it brings me back to this level. If I press the escape again, it brings me back to the home position. From a metering point of view, we can go through and check out all these different parameters. We can see a full summary. We can look at the individual current, voltage, frequency, harmonics, the status of the synchro check, energy, and demand. So let's take a look at the summary. The summary is just that. It shows us all our currents, our voltages, energy, and our power. We could even go as far as looking at the phasors. So we have a three-phase graphical representation for both voltage and current. We have a graphical representation and also a display indicating the values. Let's hit the home button here. All right, next part, the set points. Once again, listing all our settings menus. And let me go into the system. So, current sensing, voltage sensing, power, breakers, flex, curves. Let's go into the power systems just to take a look here. So things such as setting this up, the frequency, phase rotation, frequency tracking, and the cost of energy. Now, I'm not sure how accurate this is. This has been some time, I'm sure. So let me back up here a little bit. The LEDs along the bottom here, I want to talk about these for a moment. The LEDs that we have the front panel consists of 17 LEDs. This is 2 columns of 7, so 1 through 7, 8 to 14, and this is 15, 16, and 17 LEDs. These, with the 12, we have 12 programmable LEDs, 3 programmable push buttons with the programmable LEDs. The first 4 LEDs are non-programmable, they're in service, and they're the pickup LEDs. All the other ones can be programmed for 3 different colors, for red, green, and orange colors. The push buttons along the bottom, let's go here. So the push buttons here are available for programming. Their typical applications consist of breaker control, auto reclosure blocking, settings route changes. Each one of these buttons has asserts its own flex logic operand. So each one of these buttons, this is called control push button 1, control push button 2, control push button 3. And each one of the LEDs, each one of the push buttons has an associated LED. So this is 15, 16, and 17. We have environmental monitoring built in. So now that we can monitor from the relay's point of view, temperature, humidity, any surges and vibration to notify the operator that we've exceeded the limitations of the relay. Communications. So our device interface has now been changed from our serial port. We now have a USB for single relay access to interrogate the information from the relay. And we also have a Wi-Fi access available as well. So you can use either your laptop or your tablet to configure or to retrieve data from the relay itself. Let's take a look at the rugged design. So here's the breakdown of our relay. We have a field swappable power supply. It's easily removed just by turning a thumb screw on the end here. Sorry, it's on this end here. That allows us to easily remove this. We now have standard harsh environment conformal coating that is standard. It's no longer an option, it's all standard. The PCBs are designed to a class 3 manufacturing. We've eliminated electrolytic capacitors so that we no longer have to have annual power-ups of the devices to exercise electrolytic capacitors. We have a new draw-out design that allows us to come in and easily remove the relay from the case without losing a fingertip or a fingernail. Okay. Along the back, we have our connections. So here at this point, we have our different connection points. One of them here, this is our main power coming in. We've got our live, neutral, and ground. We've got one single ground connection, as opposed to on the SR relays, we had the filter ground and the safety ground. We now have one ground only. There's a single chassis ground as well. So everything ties back to this the chassis ground point. The terminals here, B and C, these are designed for our analog inputs and outputs. The analog inputs and outputs we're referring to are our 4 to 20 milliamp or RTDs. So depending on what the application is, whether we're dealing with transformers or whether we're dealing with motors, we can accommodate 6 RTDs for the transformers, 12 RTDs for the motor, consisting of a stator, bearings, and ambient temperature. From a communications point of view, now we're dealing with iRig-B for time synchronization, RS-45. We have copper connections for our communications, and also 2 pairs of fiber optic connections. Now, depending on which communications you're purchasing, if you're buying the typical communications, then you're just going to have copper without the fiber optics. If you're buying the advanced communications, then you're getting the fiber optic communications, and the copper is disconnected. So the focus is using the fiber optics. These can be configured either as independent ports or as can be used as backups for each other, or we're going to be using it for IEEE 1588 PRP. That's Parallel Redundant Protocol. We have our CT and VT connections. So 4 channels of currents, 4 channels of voltage. This is another spot for expansions, so for further inputs for voltage and current. So if we want to do differential, directional, multiple winding transformers, we have the capabilities of expanding the inputs of this particular relay. We have our inputs and outputs. So we can have up to 32 digital inputs, 16 digital outputs, depending on your configuration of your order code again. The 2 halves are separated. This is our output relays on the upper portion. On our digital inputs are located in the lower portion. We have both wet and dry type of connections for our contact inputs. All right, I think that's everything. All right, fantastic. Any questions? Okay. So, surprisingly, the 850 has the exact same cutout as the 750. Here's a table here that's showing some of the differences between the two. I won't go over all of them, but just some of the key points here. Once again, the electrolytic capacitors, the standard conformal coating, the PCB being manufactured to a class 3, 61850 is available. We have 6 settings groups. We have the Wi-Fi communications, NERC compliance, total harmonics, greater sampling for the oscillography. So there's some great features that are designed into the 850. We have higher sampling rates for the oscillography, as I mentioned before. Number of events are improved as well. Better accuracy on the protection, and the CT accuracy is improved as well. So these type of features have greatly improved the features of the 850 over the 750. Now we're going to look at some applications where we can take a look at what are some of the needs out in the world now. So one of the things here we have is an industrial and distribution electrical feeder system challenge where we're maintaining operational uptime, fast and accurate protection and control schemes. We need high-speed communications and diagnostic information and voltage surges. So, we answer the challenge by improving the protection pass time to 2 milliseconds. We introduce high-speed communications with 61850 and PRP. We introduced 2 IP addresses into the relay as well. We increased the sampling rate for the oscillography to provide better detail. And environmental monitoring to make sure that we don't exceed the limitations of the relay itself. From an industrial incoming main time main type application, we're looking at challenges such as dealing with uptime with the loss of incoming feeders. We want fast and accurate transfer of incomers. We want to minimize the required equipment and engineering time. So we answered the challenge by integrating a main scheme into the protection system. Once again, the high-speed communications is coming in handy. So we have high-speed communications between the relays as opposed to doing hard wiring. So 61850 once again allows us to cross that bridge without doing all the hardware wiring. We have built-in scheme, MTM, main time main schemes built into the programming of the relay. So the next one we have here is the distribution for the auto reclose. So the challenge here is basically a continuous system available to downstream customers. We need to re-energize quickly during transients and coordinate auto reclose functionalities. So some of the things that we can do here is we can fully programmable to block the IOC elements and to adjust the curve characteristics of any TLC element. We can adjust the number of reclose shots based on the amount of high current that's being measured. We can have up to 4 auto reclose operations with programmable dead times. The next application shows us with zone selective interlocking. So the challenge here is maintaining the high speed coordination, quickly and accurately detecting and clearing faults and reducing processor system time. Once again, the 61850 support is very important. It allows us to do this at a very high speed. We're looking at times as fast as 3 milliseconds of communications from peer-to-peer communications. So which results in fast clearing times and high-speed coordinated interlocked protection. Another application that we're dealing with is reliable detection of faults of CT saturation. So some of the challenges that we're dealing with here are slow detection of faults causing CT saturation and fast clearance of faults. So one of the biggest things that we have here, so we have 8 times per sample on the update rate. We've got 64 samples per cycle of resolution. We have a wide range for CT selection, up to 46 times the CT primary. And we have a choice of either phasor or RMS input selection when we're choosing for our protection elements. Another challenge that we have here is how do we ensure that our information, our data is actually getting back to our control center, our data management system. So one of the challenges is reducing the probability of network failure. We want to maintain high-speed communications. How do we do this? One of the ways that we can do this is by using the PRP application, which is our IEEE 1588. What it typically does is it allows the relays to output the same data through 2 fiber optic ports. Each fiber optic would take a different path. One would take this LAN path. The second one would take the other one. In the event of a break in the communications or damage or a failure in equipment, the information would still get back to the data management system. Now, the way the PRP works is this, that the first piece of information that gets there is the one that is accepted. The second one is dropped. So this just ensures that the information that is getting over to the data management system. Okay. Security. Another application, cybersecurity with radius authentication. So the challenge here is how do we keep our security intact? We have to maintain our system and operation security. We want to eliminate unauthorized system access. Well, we do this by introducing the NERC cybersecurity. So we start dealing with radius authentication, role-based access control, and password complexity. So what does this mean? Role-based access control basically means that we have to log into the relay. Depending on what your role is is going to determine whether you have read-write access or read-only access. So as an operator, you're only entitled to review information, read it from the menus, whether you're dealing with it from the front of the relay or from the InterVista setup program. Whereas an administrator has both the capabilities of downloading the information, such as event recorder, the data logger, waveform capture, all these different things are available only by the administrator. But he also has to log in as well. Now, the other thing that we have in here is that we can't have concurrent connections to the relay when we have the cybersecurity. That means either we're logged on from the front of the relay or we're logged on through the setup program. Not both at the same time. Both of them require password, are both password protected and require a login by the user. All right, here's a functional block of the 850 relay itself. So we're dealing with these kind of ANSI codes. A lot of these are very similar to what we have in the 750, with some exceptions of, the VT fuse failure is an addition, broken conductor is another additional feature, frequency rate of change. These different elements vary with the different options that you order within the relay itself. Here's the order code for the relay. So it's a breakdown. I'm not going to go into too much detail, but what we have here is the 850 relay. Right now we only have an English display. When you're ordering your relay, this is very similar to the 750 relay, where it's either you're selecting a 1 amp or a 5 amp secondary, and the same thing with the ground currents. Either you're selecting a 1 amp or 5 amp in a standard ground current or in a sensitive ground. We have currently we are offering one type of I/O card, which consists of 2 Form A's with voltage monitoring. We have 7 digital inputs and 3 Form C contacts. Now, of the 3 Form C contacts, these are our 2 auxiliaries, and the third one is a critical fail-safe output relay. So this is basically monitoring the status of the condition of the relay. If there's a fault condition or it hasn't been programmed, then this critical fail-safe relay is operational. So we know we can order 2 slots of these inputs currently. We have our graphical display, and then we start dealing with the current protection. Depending on how much protection is required for your feeder system, they break down accordingly. As we increase the choices here, the options increase as well. So one of the things that we have that are increased here, we have load encroachment, restricted ground fault, broken conductor. Okay. From a voltage point of view, once again, our standard protection takes care of these elements here: over voltage and under voltage for neutral and for phase, and frequency over frequency and under frequency. From the advanced, we start bringing in synchro check and 81R, which is our rate of change for frequency. Now, from a control point of view, you can get just something that's just the basic. When we start getting into the next level of options, we start introducing flex logic, cold load pickup, breaker failure, trip buses, and if we go to the next level, then we take those additional features and we add in bus transfer, the bus transfer. But with the bus transfer, we also need to have the advanced voltage monitoring as well. From a communications point of view, as we start increasing in the options, we get more and more features. So the base model has our front port RS-45, we have DNP 60870-5, and we have one Ethernet connection, which is our copper. When we start getting into the next option up, then what happens here is we start stepping into the fiber optic ports. These are operating at 100 megabits per second. And the Ethernet with the copper is disabled once we introduce the fiber optics. So it's not a question of either one or the other. It's either copper or it's fiber optic. When we start getting into 1P and 2E, this is where we start introducing things such as PRP, SNTP for timing. When we get to 2E, the 2E adds the 61850 option into the relay. From the fiber optic point of view, the communications that we have on port 4 and port 5, we're dealing with currently with an ST multimode with 850 nanometers with future options for the MTRL and for SFP multimode type fiber optic communications. We have Wi-Fi. This is an option. This is not the standard. So if you don't want the Wi-Fi, you don't have to order it. And the last part of the order code is the security. We can have just a basic security, or we can go right into the Cyber Sentry, which is the role-based access control. All right. So once again, from a hardware point of view, the 850 has exactly the same cutout as the 750, so no modification to the switch gear. The case is not shared between the 750 and 850. One of the questions I had earlier was that can we take the 750 and slip it into the can we take the 850 relay and put it into the 750 case? No, we cannot. It'll have to be all completely rewired. However, no mechanical modifications will have to be performed on the switchgear itself. All right, so here's where we have the user programmable LEDs. It's showing the menu associated with the user programmable LEDs. So here we have the LED number 2, which is our trip. Number 3 is defaulted to the alarm. These are non-configurable, whereas we have all our other LEDs. We have a choice of different colors and signal names that we're going to activate this. So what's the trigger? These are different signal names. Do you want the LED to be self-resetting or latch condition? And then of course the 3 different colors, red, orange, and green. Along the bottom, the push buttons as well have their own means of having when the push button is pressed, we have our own signal, which is programmable push button number 1 on. If this is asserted, then the LED will be coming on depending on which color you choose for that particular LED, or for that control push button. So here's just a further description. The push buttons themselves are also programmable to the point where you can actually indicate on the display when the button is pressed, it will actually display a message that you've programmed in here to indicate that either the push button has been depressed or whether it's been released. We can reprogram how long the push button has to be pressed for before it becomes active. So this is another option that's available to us. All right, from an electrical point of view, I'll just go into this a little bit. So here's a wiring diagram for us. We'll go into a little more detail into this thing. The one thing I want to bring to your attention is this, once again, on the wiring, the control power on this, we just have a live, neutral, and a ground connection, and there's only one connection. The ground stud, separate one, going to the ground bus. The connection between the ground to the ground bus needs to be less than half an ohm, or else the ground isn't intact. The RS-45 communications. We have a single connection for RS-45. Terminators at both ends. These are typically 100 ohm resistor, quarter watt, in series with a 1 nanofarad 50 volt DC ceramic cap. So this is eliminating the ringing in the communications. Grounding should be grounded at one end only to avoid any ground loops and intermittent communications. We have our Wi-Fi. That's also part of this slot E. And we also have our fiber optic communications and our Ethernet communications in reference to everything that's in slot E. Okay? iRig B is also available for our time synchronization. All right, from a I/O point of view, so once again, these are our terminals. So in slot F, we have in the upper portion of the relay, the terminals are labeled accordingly. So we have our trip, which is a Form A contact with voltage monitoring. We have our closed, also Form A. Our auxiliary, this is output relay 3, output relay 4, and our critical fail relay at F22, 23, and 24. Now, from a digital input point of view, we have 7 digital inputs. We can either have them as wet or dry. We can either use the existing 24 volts that it's located on the back of the relay, or we can use our own voltage source up to 300 volts DC maximum. Do not tie the 24 volts into the digital inputs. You'll damage the inputs. We have 4 transition levels that are available: 17, 33, 84, and 166 volts DC. So we can program whatever our transition level is to indicate that the item is either, for instance, a contact has been closed or it's open based on our source voltage. Now, to ensure that we have correct detection, we have 4 different voltage levels, as I described before: 17, 33, 84, 166, and they should be tied to these voltage levels: 24 volts, 48 volts, 110, 250 volts. We don't want to leave the setting at 33 volts, which is the factory default, if we're using a 120 volt DC source to control the contact inputs. This could cause a false value. So basically a false state, a nuisance condition. So it's very important that whatever the DC voltage is here is matched to, or I should say the setting is matched to the voltage source. Here's a diagram that's basically showing the trip coil supervision, how we would wire it up if we were using the voltage monitoring, and if we were using the voltage monitoring. So if we're not using the voltage monitoring, then we're using these 2 terminals. And if we are using the voltage monitor, then we need to add a jumper in between these 2 points. Now, the whole idea with trip coil supervision is this: we want to monitor the integrity between the relay and the trip coil. We want to make sure there's no breaks, but in the event that there is truly a fault, we want to make sure that the physical connection between the relay and the trip coil is in fact intact and active. So one of the things that we can do, even when the 52A is open, we can put a bypass resistor in here so that this is active even when the 52A is open. So we can verify the connection between the output relay, or I should say the relay itself, and the trip coil. We have a table here that indicates what depending on what your power supply is, the size of the resistor and the power rating on that resistor as well. Now, if we're using the bypass resistor, one of the things that we have to keep in mind here is this: under the trip circuit monitoring, there's a feature in here that we have to turn on. So to indicate that, yes, we are using this bypass breaker state, we have to make sure that this is on if we're using that bypass resistor. If we're not using the bypass resistor, it's telling the software that we're not using a bypass resistor and only become active when the 52A is closed. Otherwise, if this is enabled, it will always be active even when the 52A is open. All right, so slot J was housing our voltage and current inputs. One of the things that we have here, so we have individual contacts, polarity markings for each one of the phases, phase A, B, and C. You can see we have polarity markings for all neutral sides tied together, all going to ground. Same thing with the voltages. We have individual connections for the voltages. Both connections, the X1 and the X2, are coming back to the back of the relay. For the grounding point of view, we have terminals J, which is our standard ground. We can either use our zero sequence CT, where we're measuring ground, or we can calculate the ground as a neutral by using a residual connection. Basically summing the three-phase CTs together, summing them together to measure the neutral current. We also have a sensitive ground version of the same thing, used in high impedance grounding systems. The only thing that we have to make sure that we are using a residual ground, that we have to compensate for the inaccuracies of the current transformers. The zero sequence CT is extremely accurate and extremely sensitive, so we have to make sure that we compensate for that as well. From an environmental point of view, storage and shipping, minus 40 degrees C up to 85 degrees C. The operating, minus 40 degrees C to 60 degrees C. Humidity, 95% at 55 C. Altitude as high as 2 kilometers maximum, and a pollution degree marking of 2. So it's basically checking the ambient temperature surrounding the device every 5 seconds. So it's checking for heat as well. So what can produce heat? Things such as loose primary connections. We might have an environment where the air conditioning has failed. So this will at least alarm the operator that there's a problem. There's a problem with the environment. All right, let's go into the software portion. From a software point of view, the setup screen allows us to connect in two different means. We can either connect in through the quick connect or the device setup. If we're going through the quick connect, this is a single device connection where we can connect either in as a USB, Ethernet, or through the Wi-Fi. We would adjust the slave address to match what's in the relay, select connect, and at that point we would have a new pop-up occur and show us our connection. We would have a note indicating we have a successful connection, hit OK, and then we would have this coming up on our main screen. If we're going through the device setup, this is the other screen. This is used for multiple configurations. The same as it is before with our other devices, where we add a site, we add a device, we go in and then we can name our device, we can select our interface, whether it being USB, Wi-Fi, or Ethernet, indicate our slave address. Here we press the read order code, where at this point the software goes out to the relay, extracts the information directly from the relay, populates the order code field and the version field, which is the firmware version, and once this has been successfully completed, we can hit OK, and then this gets populated back on the main screen with these particular names. All right, so from the online window, we have this is our main directory. We have device definition, status, metering, quick setup, set points, records, maintenance, and the 61850 configurator. So we'll touch on each one of these. I'll start off with the quick connect. The quick connect allows us to go in and actually program some of the more basic settings. So things such as in service, the ready setting. When the relay first comes out of the box, this in service setting is set to not ready. So on the front of the relay, you will get an alarm indicating that the relay is not programmed, and will not clear until this has been changed from not ready to ready. We can set up our frequency. We have this is where we would set up our current and voltage sensing. So the voltage sensing, we have the choice of either going in as a Y or a delta configuration, which set up our VT secondary, ratios, and also the auxiliary connection. We have some basic settings here: trip overcurrent, phase instantaneous overcurrent, the ground time overcurrent, and the ground instantaneous overcurrent, and as well as the neutral time overcurrent and neutral instantaneous overcurrent. I'll go more into this shortly. We're going to get into the real-time clock located under device. The real-time clock is designed to make sure that we have accurate timing, especially when we're dealing with high-speed communications. We want to make sure that the timestamp that's associated and the references to main protection and backup protection are adequately recorded with the correct time base. So we have these different choices of time sources. Our PTP, which is our parallel time protocol, has the highest priority. IRIG-B being the second. SNTP, the simple network timing protocol, being number 3, and then of course the internal clock. So the way the PTP works is basically it allows us to go in and well, first of all, we turn it on. So here's the settings for port 4, and it's basically looking for a reference from a Grandmaster clock that all the clocks would be synchronizing to. Now, in the feature here, we also have some time delays that are available to us. So if the lines that are going through the two different networks aren't exactly the same length, we can actually add in a compensation time so that the speed at which the signals go to the DMS, the data management system, are exactly the same. So we can add in time delays, we can compensate for different types of propagation, and the SPP, basically we can go in and indicate, look for the Grandmaster clock that has a worst case error of plus or minus 1 microsecond. From the SNTP, we would indicate the IP address of the server, the UDP port number, and the source port number. So the source referring to port 4 or port 5 on the back of the relay. These are our fiber optic ports. From a security point of view, this is role-based access control. If you order the cybersecurity, when you come into the relay, this is the first thing that it'll prompt you for. It wants to know whether you're logging in as an administrator or an operator. And once again, the administrator has read-write access, the operator has read-only access. You need to log in either through the front panel, or you can log in through the software, but you can't do both at the same time. The default password has been left at 0. So you can see what we have here. We can indicate if someone loads in the wrong password after this many attempts, this is a programmable, then we will lock them out for a certain amount of time, or once they've logged in, how much time will allow them to remain within. So this is what the access timeout is. We can lock out the set point access as well, based on the administrator rights. Cybersecurity. So once again, we're dealing with cyber sentry security, which basically puts into place authentication, authorization, accounting remote authentication for using dial-in user services. This is our Radius client, and logging in through our role-based access control. We have security events. They're recording it through a system log so that we can monitor what's going on, who's logging in, when they're logging in, what they're changing. So this is known as SIEM, Systems for Centralized Cybersecurity Monitoring. And then we can also have encryption that we can select, where we start going into using SSH protocol, AES, the Advanced Encryption Standard, and 128-bit keys, known as the GSM or Galos counter mode for encryption. All right, so here's a little review of the roles for the access. The administrator being able to read and write for all settings and commands. We have the operator. He only has read access only. And the observer. We have a third one, the observer. He has the read access only to all the settings and has unlimited concurrent access. So that means as an observer, you can go in and log in through both the front panel and through the software at the same time. but you have, once again, no write access. You cannot download any settings whatsoever. Any settings, you cannot retrieve any information such as event recorder, data logger, oscillography. Okay, once again, this is a screenshot from the setup program itself. Just a reiteration of the features that are available within the role-based access control. All right, so every time if you have the cybersecurity, this is what you're prompted with every time you try and get into it. So security prompting you to basically log in and enter your password. The cyber sentry, so the radius server, once again, if you have this feature in place, putting in the necessary information for the radius server. At this screen, we can also go in and we can change the passwords. So if changing them from the factory default of 0, you can make them as complicated as you wish. What to do if somebody's trying to, if authentication fails, how long to lock them out for, whether we want to go into using password complexity, set point access. Okay, so from a communications point of view, let's go into the Ethernet now. From the communications point of view, from the Ethernet, we have 3 different choices. We can either set the ports 4 and 5, the 2 fiber optic ports, as operating independently of each other. Each one of them has their own IP address. They would be operating at 100 megabits. One of the things that you have to remember with the relay, that once you change the IP address, you've got to reboot the relay, or else the settings won't take effect. The link loss alert, basically what happens here is this. This acts like the one of our other products, where one port is active until there's a break in the communications, then it automatically switches over to port 5. So one port is active only at one time. Both ports share exactly the same IP address, subnet, and all the other information that we have here. And we have a break in port 4, and automatically switches to port 5. If it recovers the communication in port 4, then it automatically switches back to port 4. From the parallel redundancy protocol, once again, the IP and the MAC addresses are shared between the 2 ports. The idea here is whichever one receives, at the data management center, whichever data is received first from either port 4 or port 5, both of them are identical. Whichever one is received first, the data management center, is the one that is used. The second one is dropped. The Wi-Fi communications. So this is the screenshot from the Wi-Fi. It allows us to turn it on or off. We get to put in the IP address of the relay itself, the address of the gateway, the IP address of the gateway, the security level that's being used, the SSID for the gateway, and the password within the gateway itself, the passphrase. Now, how do we know if this is actually working or not? One of the things that we have on here is in the setup program, there is an icon that appears in the upper left-hand corner that basically has these 4 different states. The first of them is disabled, so it's basically the icon is turned gray and it's got a red line going through it. If it's disconnected, it's gray. If it's trying to connect, then it's a yellow color. And if it's finally connected and you're successful, it's green. From the interface, this is the kind of information that we see for device definition. So I connected to the relay using the Wi-Fi interface, and you can see the type of information that we're getting here. We get the order code, which is standard. We get our version. We get the serial number of the relay itself, and we see how we're connected. So in this case, we had a Wi-Fi connection with this specific IP address, slave address, and this particular port. Let's go into the transient recorder next under communications. So the transient recorder, also known as the oscillography, needs to be programmed. If we don't have anything set up for a trigger source, we will not be retrieving any oscillography, so it needs to be set up. We can record up to 32 digital inputs and 16 analog values as well. We can adjust the sampling rate between 8 to 128 samples per cycle. Of course, the higher the sampling rate, the better the resolution. Now, the way this thing works is this. We can maintain the number of records that we're going to maintain in memory. In this case, we're looking at 16. We can adjust the number of samples per cycle. We can indicate the trigger mode where we want to be in a protected mode or overwrite. So protected basically means that if we have this many records recorded, then once those 16 have been filled, we will stop recording any further. If we do an overwrite, we will keep on going with a buffer window of 16 waveforms. Our trigger sources can be any type of signal that we want. We can have flex logic. We can pick up on any type of a pickup. We can trigger on any type of an operate signal, on any trip condition, or even on any alarm condition. So we have all these different choices available to us. Underneath here, we have our 32 digital inputs where we can program different conditions. You can see here we have pickup and operate. So why is this important? Because while we're recording the waveforms, so recording 5 current and 4 analog channels of waveforms, we can also see the operation of when for instance, the phase time over current condition picked up. The fault condition would be recorded, and then how long it took the relay to actually operate. The second part of this is the analog portion.
Hey, George.
Yes.
Gustavo, I have a question here. I don't know if I can. If you go back there, yes. When you, for example, if you turn on trigger on any pickup, do
Yes.
automatically all those pickup you program show up as there, or you have to do one by one?
No. So what it does is in any of the programming, it's going to be referencing for every protection element. We have 3 different signal types. We have pickup, we have operate, and we have dropout. So any time that pickup flag is set, then it's going to trigger the oscillography if you select it in here. So you don't actually, it's just indicating whether it's off or on. Here, let me show you. One moment. Let me go right into the relay itself. So here's the relay. Here's the setup program for the Series 8. So if we come into the device setup, under the transient recorder, we have, right now it's defaulted to 5 times. We have our trigger position. The trigger position is based on the number of waveforms that we're capturing, how much of it is pre-fault information. So now let's take a look at the any pickup. So it's either off or on. Okay, good. The trigger source is all our different flex logic elements.
Thank you.
Okay, you're welcome. All right, let's go back. Analog values, so we can monitor any one of the RMS values, the phasers, so anything that's analog values that we could record here. I've got a couple examples here. We're looking at some current inputs and arcing current and some voltage inputs. All these waveforms are stored in non-volatile RAM. So what does this mean? This means that even though we cycle power on the relay, we will not lose the waveforms. They're stored in memory. Okay, so this was an issue with the SR750 or with the SR relays, where if you cycled power in the relays, you would lose the waveforms from memory. All right, breakers. In the breaker section, we have an opportunity to name the breaker function. We can go in and we program in the input statuses for the 52A, the 52B, and also for whether we're connected to the breaker or not, so as like a racked in or out type of signal. Based on these inputs, we have a choice of either we'll get different types of configurations. So if the 52A contact is configured, we have these different choices available to us. And these are the different signals that will be recorded also into the event recorder if we choose to go that far. If both of these are the configuration set to null, then obviously the breaker is not configured. So here's where we're showing the statuses. So if this is open, if the 52A is open and the 52B is closed, then it's going to give us a status of it being opened. This configuration closed. Hopefully we'll never ever see this in our lifetimes where both the 52A and the 52B are both showing the same state. This is definitely undesirable. The flex curves. Now this is an interesting feature that we have here. We've got 4 programmable curves that we can configure. The points on the curves are configurable by the user, and I'll show you an example in a minute. We have 120 points that we can modify. 40 of them are for reset and 80 of them are for operation. And now let me just show you this because this is a really interesting feature. So this is what the screen looks like. We have our elements here and values, and then we also have our screen. So let me just drop into the actual flex curve portion. Whoops, I'm in the wrong section. There we go. All right. So let me modify this. I'll just move this over so we can see more of it. So what this allows us to do is pick out the curve of our choice. Let's stick with the extremely inverse. We can initialize this. So here's the type of curve that we have. Now we can either modify the appearance of this curve either by coming up in here and making the changes accordingly, or we can actually grab the individual points and modify it as needed to match our coordination study. The information here updates as we move the points. Okay, how about that? That's a great feature. And you can go in there and save it. And then now this flex curve can be used for any of the protection element, for the TLC protection elements. Okay. Inputs. So in this area, this is where we would label our inputs. We have our 7 contact inputs. We would set up our voltage threshold in here, debounce time, signal names, and whether we want to record the transition every time it opens and it closes. So let me just go back to the relay for a moment. So from the relay point of view, we have our inputs, we have our contact inputs, for instance. Now my relay has 2 contact input boards. We can adjust the voltage levels by clicking in the box. 4 voltage levels. We can come in here and name the individual contact inputs. We can adjust the debounce time anywhere from 0 to 16 milliseconds. I think 2 is typically typical defaults. And then we can also determine whether we want this to be recorded in the event recorder every time the status changes. Okay. Let's move back. We have virtual inputs, 32 virtual inputs. So we have contact inputs, which are hardware input, and then we have virtual inputs, which are a software input that we can configure, once again, either as latched or self-resetting. We can control the virtual inputs. We can name them. We can record them into the event recorder. So one of the things, let me just have it go back for a moment back to the relay. So from the contact input point of view, we not only have the programming portion of it, but we also have the status portion of it, where we can monitor the actual status of the contact inputs. Here's how it looks. I have an RTT connected to my relay currently. So just as I'm closing switch number 1, This is the status that we're seeing. Okay, closing the switches, or sorry, opening the switches. This is our configurations. Now, we can do the same thing with the virtual inputs as well. So as far as the inputs are concerned, the virtual inputs are controlled a little bit differently. They're turned off by default. I have to switch them on to make them functional. I can give it a name. I can have it either as a latched or a resetting type configuration. And we'll save this, and I'll just show you how this operation works as well. So monitoring the status of the virtual inputs. And our control is done by under our control section for our virtual input control. So here at this point we can come in here, make our necessary changes. And that didn't work. Wonderful. All right, I'm not sure why that didn't change states. All right, I'll have to investigate that a little bit later. So to close all the windows at once, we can go up to window, close all, quickly closes everything off. The remote inputs, these are used for the 61850. It allows us to go in and name the individual remote inputs. So these are the goose messages that we can assign, and these are all assigned within the 61850 configuration that allows us to go in and monitor the status, use this for flex logic, use this within our flex logic. Output relays. We have our trip and close, which are adjustable from 0.01 seconds up to as high as 9.9 seconds. We can have blocking signals coming in here to block this from operating. We have auxiliary 3 and auxiliary 4, which is configurable, where we can set the signal here to indicate which signal is going to cause the output relay to energize. We can have it self-resetting or as a latch condition, and also record this in the event recorder. The trip and close will operate in less than 8 milliseconds, continuous current for 10 amps, and make and carry 30 amps. Aux relay 3 and 4, same kind of idea, less than 8 millisecond speed, continuous current of 10 amps, make and carry 30 amps, and this can operate on any digital signal. All right. Virtual outputs. Virtual outputs are the resultant of our flex logic. So if we set up some logic where we're trying to control an output relay, or we're monitoring the status of inputs, either from contact inputs or from a second relay, the virtual output is the resultant of our Boolean algebra that allows us to assign, that we can assign this virtual output to either an LED or an output relay operation. We have 32 of these that are available to us. All right, so I'm going to step into the protection here. We'll talk more about this flex logic here. I'll give you an example of the flex logic. Now, from a protection point of view, we have 6 protection groups, each one of them containing current, voltage, and frequency. We can switch between groups by selecting any digital input, flex operand, push button, or communications. So we have a means of either going through the menu structure here or selecting this hotkey that we have here. So let me just open up this protection summary. Let me just go into it live so we can see how it looks. So here's our icon here. It's the third hotkey from the left. It's now going to open up all our protection elements that are available within the relay. Okay. One of the things that we have here, we have our 6 individual groups. If we want to see more of the group programming, it allows us to do so by clicking on the checkboxes. So let's just keep this simple. If we're dealing with 2 different sets of cards, then of course the features increase as well. Now, let me explain something that's going on here. This F7 and F10, G1, G4, G7, G10, G22, these are the physical connections on the back of the relay. So these are the common points for the output relay. So this is for aux3 and aux4, and then G1, G4, G7, G10, G22 is on the secondary I/O card. So we can assign the different inputs to operate on those as well on top of the trip or alarm. So if I go in here and program the phased instantaneous overcurrent, for instance, it automatically takes us into that screen. It allows us to select one of the 4 choices: trip, alarm, latched alarm, or configurable. So the trip, self-explanatory. The alarm is self-explanatory. Latched is self-explanatory. The configurable means that it will still execute but won't be recorded as a trip or an alarm condition. We have a choice on the inputs as far as phasor or RMS values. We have our pickup values for the current, anywhere from 0.05 to 30 times the CT primary for pickup levels. We can introduce pickup delays if we're doing coordination studies. We need to have this as backup protection. We can have a reset delay if we need to have the breaker cool off, so that we can introduce a delay before we can reset the relay. We can have blocking signals. Once again, these are all our flex logic elements. We can determine which output relay we want to operate in addition to the trip or alarm or whatever we've configured, and the events being recorded, event recorders, and the targets, whether we want this to be left on the front of the relay, whether it's going to be self-resetting or a latch condition so the operators can see it. All right, so let me come into this. So what happens once we got this configured, then it allows us to go into the light turns green. We have choices here whether we can look at all the elements at the same time or enabled. Actually, let me just change this to tripped. Let me just turn this back. Let's save this as a trip, because that's what it is. Typically, short circuit needs to be closed, shut down as soon as possible. So what we have here is this. We can see the features that have been turned on by themselves. And one of the features that what I'm going to do is I'm going to actually produce an instantaneous overcurrent condition here. One moment. Sorry, my trip level's just a little bit too high. I'll set this as latched. Okay. I'm just going to go into my event recorder. So the event recorder is this is the hotkey for the event recorder. Allows us to come in here and take a look at all the configurations that have occurred within the relay itself. Contact closures, contact opens, the critical fail if it's been turned on, output relay switching on and off with a date and timestamp down to the microsecond. So we're looking at 6 decimal points for time. Let's go back for a moment. So this is where the F7 and F10 was coming from. So this is the actual physical termination on the back of the relay. So we're looking at the IOC, showing us our different values. The difference between phaser and RMS. Now, the difference between the two are this. The obvious one is phaser has a magnitude and an angle. The RMS is just a magnitude. Now, in further detail, the phaser is only the fundamentals. So all the harmonics have been removed. From an RMS point of view, it includes the fundamental plus all the harmonics. Okay, and I think we've reviewed everything else here. Under the monitoring section, this is where we'd go in and we would select our different points. We wanted to look at digital counters, pulse outputs, demands, configurations, breaker arcing, circuit monitoring. So our voltage monitoring would be configured in this screen here. Control elements. So we have in our control element section, we have these different features here: the trip bus, the breaker failure, manual close, cold load pickup, under voltage and under frequency restoration, and VT fuse failure. Now the trip bus, I'm going to go into the trip bus because this is an interesting feature. The trip bus, let me switch everything back on. When we switch into the trip bus, one of the things that this allows us to do is this. We can go in and physically select different parameters. So let me just type in, phase TLC1 operate, for instance. I'll do the instantaneous overcurrent as well. So this is nice that we can actually type it in. We can indicate, so there's up to 16 inputs that we can put in here. The trip bus is a 16 input OR gate, where if any one of the inputs goes high, the trip bus signal goes high. Now, this is an input that we can use for flex logic programming somewhere else. We have the choice to have it as a latch condition. We can set it up as a latch condition for targeting on our target, so on the front display. We can record this in the event recorder. We can also have other output relays operating it and blocking it as well. Now, this is not a typical signal that you would want to have latched on the front of your display, only for the simple reason is when the maintenance people come running up to it and they see a trip bus condition, they won't know what it's for. So this is more for the engineer who's doing flex logic and needs additional logic. Okay. So let me come back to the presentation. So this was the control bus. So we have 6 identical, all doing the same effect. Trip, alarm, or other logic actions, latch, delay, sealant, delay. These are all available. So these are all the different options that we have. All right. We have digital counters built into this thing as well. The digital counters, which is down here, we're just monitoring the status of an element, whether we're looking at a contactor changing states, or breaker, or counting pulses from a watt-hour meter, so, or an external closure of an output relay. So these are the different things that we can do with it. We can set up a value that if it reaches this value, this is our compare, that we can produce an alarm condition or energize an output relay. There are flex elements that are associated with it. So the low signal means that we're below our compare value. Equal means that we've achieved it, and then the high means that we're above it. So you could also configure your LEDs on a front panel to monitor this as well. All right. The flex logic. So from a flex logic point of view, we have 32 timers available to us for flex logic. we have a time delay on and a time delay off. This is what the pickup and the dropout are referring to. We can set it up in milliseconds, seconds, or minutes as far as timers are concerned. Each timer can only be used in the flex logic. Can only be used once within the flex logic. The flex logic equation editor, so we have 1,024 lines of logic. One of the things that allows us to do is it uses reverse Polish notation. So if you've never used this before, the idea here is this. If we want to configure this where we have two inputs operating on an exclusive OR, that means either only one of them can be closed at one time. We basically have to list our items that we want, the parameters that we want to deal with, and then the next line is what the function is, and then to close the subroutine is selecting assign virtual output. We also have a graphical representation. If you select view, we can also see the graphical representation where it shows you what the equation was that you programmed, and you can also put comments in here indicating what the different lines represent. So line 1 racked in, it refers to this. The breaker 1 52A status is the second contact input, and then what the resultant of the virtual output is, indicating device online. Same thing with here's another portion here where we have any trip. That means any trip condition. You don't have to indicate which one it is. If any of the trip conditions occur, when the reset occurs, there's a time delay of 60 seconds that's been incorporated here, so it won't the signal will not drop out for 60 seconds. Or if we manually close it, we can make this virtual output go high as well. So basically what they've done is they put a little comment section for each one of these. So this is a great little feature that we have here with the comment section. So before I go there, let me go into the flex logic so you can see what it looks like.
Hi, I have a question.
Go ahead. Yes, please.
Whether the comment is impacting on the quantity of line of the logic?
I'm sorry, repeat the question.
If we add a comment, whether it's counting as another line in the flex logic?
No.
Okay, thanks.
No, it does not. Very good question, because if we're limited to 1,024 lines, then if the comments are taking up some lines, it defeats the whole purpose for us, doesn't it? So here's an example that I created. So contact input 1, contact input 2 being on, and here's my comments that I put it on, what it's referring to, my function, the exclusive OR, and to close the subroutine, assign virtual output, and giving it a name. So when we go into the view mode here, that was interesting. When we go into view mode, then we can actually see what's going on here. So we get a graphical representation of what's going on and with our comments below it. Okay. For the conversion, so because the 850 is a direct replacement for the 750 relay, we've come up with a tool that allows us to import the 750 file. So we can import the 750 file and convert it directly into an 850 settings file. It will come back and show us what was successfully converted. So basically with the parameters, the values that were the original settings, and what is in the new settings for the 850. So here they have an example of the current transformers, the voltage transformers, the elements in the power system between the 750 and the 850. This file is then saved in the offline window with the CID extension. So when we're going into this, let me just show this to you. In the offline window, So when we right click on the word files, we have three choices. We can add a new site, we can add existing settings file, or a new settings file. So regardless of which one we use, oh, sorry, my mistake. When we go to a new settings file, we have our choice to create our new settings file here based on pull downs. We can pick and choose our order code, save in a specific location based on the click of the dot with the square with the three dots, give it a name, and it has the CID extension. If we want to import a 750 file, we can do this. We'll select the box with the three dots. It will prompt us whether we want to work with 750 or 760 files. Once we select what we want to work with, then we'll highlight the file, click on open, and then it goes through the process of doing all the modifications. And then once the modification has been completed, it will then populate it here in the offline window. All right. Now, coming down to the creme de la creme, we have the IEC 61850 configurator. Now, with the 850 relay, the 61850 configurator works with both analog and digital signals. We're monitoring the status of the inputs, outputs, protective elements. It's updated every 2 milliseconds. We can publish up to 3 goose messages, and we can subscribe up to 8 goose messages. We also have where we transmit as soon as a digital point changes states, and for the analog values, because we don't want to bombard our network, we can have a deadband programmed in so that it won't transmit except once we exceed the deadband. Now, I'm going to demo this for you. One moment. So what I've done here is I've created 2 settings files, feeder A, feeder B. When we expand on this thing, one of the features that are built into this thing is the 61850 configurator. When we select this, here's the appearance of the screen. So here's our ICD CID file for feeder A. This is typically defaulted to the word template in uppercase letters. If we click on this box, wonderful. We have the ability to come in here and change this naming, the ID name. Remember, in our network, when we're doing 61850, every device has to have a unique name. The naming convention is extremely important when we're dealing with IED naming. We can't have a space between the words. We can have an underscore, is fine, no spaces, no dashes. When we come into the settings, this is where we can come in here and program once again the name of the name of the device, what the device is. We set up our deadbands for our different parameters. You can see here we have our deadband for our MMXU, which is our meter devices. This one is for watts. This one is for VARs. Apparent power, power factor, frequency. The list goes on. We have all our different metered values here. We will come in here and program what our deadband is before it'll transmit an analog signal. This portion refers to our virtual inputs, how we want to handle it, whether direct with normal security or just monitor status only, and circuit breaker status. How long of a timeout we will allow for a breaker failure signal. We can create and our transmission. So this is the publishing side. I'm going to jump straight to the transmission side. So the way this is done is we come down here to the Add Goose Control Block. So we get the screen that appears. We can give the control block a name. I'll just leave it at default currently. And the goose ID is the name of the goose message. So let me just change this. I'll change this to the 850. I'll call it feeder A. So this now gets updated with that information. Down here, we have a list of all our logical nodes. Each one of these are listed as per the 61850 standard. So let's pick something that we would recognize. Say something such as in the MMXUs. We can see all our parameters are here. We have, let's take a look at the amps, for instance. The amps, we can look at individual phases, the neutral. So let's take a look. Let's take this one. Let's take the auxiliary, the phase A. We can look at the instantaneous value, or we can look at the one that deals with the deadband. So there's a difference between these two values. If I stretch this further, I can look at the magnitude or the angle. So let's say I want to look at the phasor value of this. So all I do is grab it, drag it over. It is already populated. We can see the logical node. We can see the functional constraint, the attribute, and then the data. So this is the data attribute, and then finally the data itself. If we grab another device, let's do the same thing, say with the voltage. So we have phase-to-phase voltage, or phase-to-ground voltage, or we have phase-to-phase. Let me just grab the phase as well. Same idea. I'll grab the magnitude, drag it up. So now we've got two values here. Let's grab a protection element. Phase instantaneous overcurrent. So with the phase instantaneous overcurrent, we have, once again, these are different features that are required for the 61850 standard. This is mode, behavior, health, and these are all based on the relay, or on the function, whether the function is enabled, whether it's disabled, is it valid data, invalid data. We have two configurations here. We have one called start and operate for the protection elements. The start indicates the pickup. So if we look at, when we open up for the instantaneous overcurrent, we have general, which is any one of the three phases. We have directional, we have phase A, B, or C. Let me just grab the general. We'll just drag it in. So now we're looking at instantaneous overcurrent. We have quality stamps and time stamps as well built into this. If I want to record when the trip occurs, then I can just grab this, drag it in as well. So there we have some points. Phase instantaneous overcurrent, I'll do the same thing with that just quickly. So the pickup, and finally the trip. Click on save. This is now being recorded. So this is now completed. Now, this was number A. I'm going to go over to feeder B now to configure it, because I don't have anything that's being published on the other settings file, and I can't add anything because there's nothing to add. If I go into feeder B, there's no goose messages that I've configured yet. So just one moment. When I close this, so as I open up the second one, all right, I'll set up a couple of transmissions. So once again, adding a control goose block. I'll just call this feeder B just to give it a different name. Once I click away, this name now comes into effect. Once again, all of my logical nodes are listed here. I'll just put in a couple here. I'll just put in the instantaneous overcurrent and the time overcurrent on this one, just to put something in. Just a repeat of what we did before. Operate. And I'll also do the time overcurrent. So here's the pickup. And I'll also go into the operate under general. Okay, that's fine. So we'll stop there. So this is what this is what this relay is going to be publishing. Now, from the reception point of view, how do we do this? First of all, we need to add the ID. So we're dealing with right now with the feeder B relay. So let's load in feeder A. Here is our goose message. Here are all the different data points underneath that goose message. So depending on which one I'm interested in, let's say I'm interested in the instantaneous overcurrent, just the operate, just drag it over. I'll grab the time overcurrent. I populated it with the wrong one. My mistake. I'll grab the second IOC as well. If we want to add an additional goose message, we can just come in here. I don't have another one to provide in here, so it would be another relay. And basically what you're doing here is you're just saving this, and your mapping is now being completed. Okay, you would close this down. These settings would now be loaded into the relays, and then the mapping has been completed. Now, one of the things I didn't look at, one of the things I didn't mention here, let me go back to the transmission. There are only 3 goose messages that we can work with. If I try and add a 4th one, it produces an error. So this is the maximum amount, so there's no question about completing any further. It won't let you do it. Same type of configuration. To remove them, right click, you'll get a remove goose control block, and it'll allow you to remove them. All right, so let me come back to the reports. This is something I skipped over on purpose. So, from a report point of view, we can either have buffered or unbuffered reports. Now, what's the difference between the two? Buffered reports are basically, they're going back to your data management system, but if we lose communications for whatever reason, the information is stored in a buffer. In the unbuffered report, so going back to the buffered. So if we lose communications in a buffered report, it will store all the information in the buffer. Once the connection has been reestablished, whatever information has been stored in the buffer will be transmitted to the data management system. In the unbuffered report, if we lose communications, the data is lost. It's discarded, even after the communication has been reestablished. So that's the difference between the two. So if we go into the buffered report, let me generate one here. So new data set. You can see this is very similar to the other screens that we were looking at. We can have a name for the buffer. We can indicate in here which parameters we want to be using within this buffered report, going back to the data center. I'll just grab one just to keep it straightforward. And this is how we build our reports using this 61850 configurator. So once we saved it, this is now part of that report. Okay. That's it. All right. I don't have a second relay to show you the interoperability with this right now. So this completes our introduction, our webinar on the 850 relay. Now, are there any questions?
Yes, George. I
Yes.
have a few questions. This is Gustavo Brunello.
Yes.
First of all, if you go to the the hardware, the input screen, where you show in the Mac machine interface, the configuration of the inputs.
Oh, inputs? So you want to go here?
Yeah, please go there. You can go there.
Okay.
Yeah, open there. Inputs, contact inputs.
Certainly.
Okay, there. Okay, I have here to set the voltage threshold,
Yes?
which tells me what ones for slot F or slot G.
They're for both.
Now,
If you,
yeah, but now then it goes contact input 1 to 9. How do I know what of those inputs are in slot F and what are those in slot G?
Okay, very good question. Each one of the I/O cards has only 7 contact inputs. So the first 7 are related to board F, and 8 through 14 are referring to slot G.
I think they should have made a better job if they did as in the UR, in which each contact input was referred to the slot and to the input number. But okay, the same goes for the contact output. I think
Oh, you would like to see a reference to the actual physical
they should
connection.
put, F1, F2, F3, F4. Anyway, that's it.
That would be,
Let's go to the
yes?
Go to the trip bus, please.
The trip?
Trip bus.
Okay. Okay.
Yeah, this go at the top. Okay, again, this F7, F10, what are those?
Okay. Excellent question again. So the connection on the output relays, the common of the Form C contacts are these points. So let me just grab my diagram here. I have a diagram that shows the. Okay, so on the output relays, the F7 connection is the normally closed contact. It's auxiliary number 3. The F10 is the normally closed contact for auxiliary number 4.
Oh my goodness.
Yeah.
Okay, well.
So in other words, in a nutshell, what this is representing is, in addition to the trip contact closing, we can also have auxiliary 3 and auxiliary 4 energizing as well. That's all it's referring to in simplicity.
So that is in the slot F, position 10 or terminal 10. What's
This
that
is
thing?
yeah. So this is an F. So this is output relay aux 3. F10 is aux 4. If I was to bring up the G's, then these are the additional output relays.
So those are the slots or the position, the physical position where these stuff are.
Correct. This is the physical terminal connection on the back of the relay for the the relays.
Oh my. Okay. So which is in addition to the trip.
In addition to the trip, that's correct.
Okay. Now, if you go to the 62050 configuration, please.
Okay. Let me close this down.
Sorry, guys, I have many questions.
You're probably answering some of the other questions for the other guests as well.
Now, if I want to send, you show how to map a goose from a protection function and how to put an analog goose. How do I map a virtual output, for example, on a transmission? I want to transmit the virtual output. Where are those?
Excellent question, Gustavo. Excellent. One of the things I didn't mention is the the general and generic inputs and outputs. So when I pull the cursor over it, it tells me what these are for. Here's my contact inputs, our GGIO2.
Contact inputs.
These are contact inputs. GGIO3, one moment. So GGIO3, this is our virtual inputs. And last but not least, well actually there's a couple more here. So GGIO4 is our virtual outputs.
The 4 are the outputs.
Number 4 is the virtual outputs. Number 5
Which I think are different
is our remote
than the
inputs.
UART, because the UART is different, eh?
It is indeed. In the UR, we're actually using GGIO1 as well. So 1 was the publishing. GGIO3 was the subscription. GGIO4 on the UR was
Whatever. So these
Whatever.
are different from the UR.
yes.
Eventually, the new UR will follow this convention, I hope.
Yes, it will. That is my understanding within
Okay.
firmware release 7.6?
7.3.
7.3?
Okay. Thank you very much. I have no more further questions.
Okay, fantastic. Anyone else that has a question?
Maybe I was the only one on the line.
Oh, it appears that way. All right. If there's no more questions, then I would like to thank everyone for attending the 850 webinar. Thank you very much, everyone. I just want to let you know that this is being recorded, and it's going to be available on our YouTube channel by approximately February 21st. Okay, we will send you the link to it if you would like it.
But okay. By the way, okay. Then we will talk, George. Thank you. Bye bye. Good night.
Okay, have a good night, everyone.
Yes, right.
Bye bye.